Hello, George Romanic here. Today we are going to look into the physics of elastic collisions. What is an elastic collision? It is a collision during which the total kinetic energy of the system stays conserved. This doesn't have to be the case always, and the other type of collisions where the total kinetic energy is not entirely conserved is called inelastic collisions. In perfectly elastic collisions, let's say we have two balls coming in, they collide and they bounce off. Velocities before and after the collision will probably be different for these two balls, but the sum of their kinetic energy stays the same. In inelastic collisions, that doesn't have to be the case. For example, as these two spheres collide, they can stick together, and therefore the kinetic energy is not conserved before and after the collision, but part of that kinetic energy goes into the potential energy, vibrational energy of these particles and so on. In this series of videos, however, because currently we are dealing with kinetic theory of gases, we are interested in perfectly elastic collisions. And then if we have a gas in which particles are approximated as small spheres, and they are jiggling all over the place and bouncing against each other, if we say these collisions are perfectly elastic, there is no loss of kinetic energy, we would call that gas ideal gas. Without any further ado, let us now develop mathematical theory of one-dimensional, perfectly elastic collisions. Say we have two atoms in a gas. Here is atom 1, and over here is atom number 2. Atom number 1 has mass m1 and this one has mass m2. This one has initial velocity in this direction. Let's call it v1 initial. So this is 1, this is 2. And let's say that doesn't really matter. Maybe this one, they are going head on. This one has velocity v2 initial. So this is before collision, and now after collision, so collision somewhere here happened, maybe this is collision, bang, collision happened, and now this particle number 1 is moving, let's say, in this direction with velocity v1 final, and particle number 2 is moving in this direction after the collision with velocity v2 final. Here we are assuming that masses are still the same, m1 and m2. Mass is conserved, and as you can see, we are using one-dimensional case over here, so that we don't have to use vectors, and we simplify our derivation a little bit. Now immediately you might say, how do you know that after the collision particle 1 will go in this direction and particle 2 in this direction? Why not particle 2 continuing in this direction after the collision? The answer is I do not know. I just drew these arrows arbitrarily, but the theory that we will derive over here that includes conservation of momentum and conservation of energy will make sure that the final result has the proper arrow depending on the masses and velocities. So to develop the theory, let's say that this is positive x direction, and we know that two laws that are always conserved is the conservation of momentum. So momentum before collision must be momentum after the collision, and because these are elastic collisions, kinetic energy before collision is equal kinetic energy after the collision. This need not be the case if the collisions are not elastic. So these two fundamental principles of physics will be used to derive the unknown velocities v1 final and v2 final. So we are assuming we know initial velocities and masses. What are the final velocities after the collision? Well, if we write conservation of linear momentum, we know that before collision, mass of particle 1 times velocity of particle 1 initial plus mass of particle 2 velocity of particle 2 initial needs to be the same after the collision, namely mass of particle 1 velocity of particle 1 after the collision, and plus mass of particle 2 velocity of particle 2 after the collision. At the same time, we know that the law of conservation of kinetic energy also holds, so that means 1/2 mass of particle 1 velocity 1 initial squared plus 1/2 mass of particle 2 velocity of particle 2 initial squared needs to be m1 v1 final squared 1/2 plus 1/2 m2 v2 final squared. There are so many indices here that I envision that I will mess up indices somewhere. I'll give my best not to do so, but let's see. Now, in these two equations, we have two unknowns, and these two unknowns are v1 final and v2 final. On many YouTube channels, they would tell you that now you can manipulate these two equations and they will give you the final result. But this is not what we do on my channel. On my channel, we will grind and actually, in front of your eyes, manipulate these two equations so we get expressions for v1f and v2f. To do that, we will start by kinetic energy equation. First of all, we can multiply it by 2 to remove 1/2 everywhere. But more importantly, what we will do here is we will group terms around masses. So, around mass m1, I have v1 initial squared minus v1 final squared, and that is equal m2, and next to m2 I have v2 final squared minus v2 initial squared. Now we will factor these binomials and write that m1, this one is v1 initial minus v1 final times v1 initial plus v1 final equals m2. Now we will do the same for the momentum equation, namely we will factor terms around masses m1 and get v1 initial minus v1 final, and that is equal m2. M2 has v2 final minus v2 initial. Now, if we divide these two equations, you will notice that these masses will cancel, and you will also notice that this term and this term will cancel, as well as this term and this term over here. So what we get is that v1 initial plus v1 final is equal v2 final plus v2 initial. Or from here we can calculate that v2 final is equal v1 initial plus v1 final minus v2 initial. However, I still do not know v1 final to be able to say that this equation is satisfactory. But what we can do is to plug in this equation in our initial momentum equation over here, and if we do that, I will continue here, we will get. And now, instead of v2 final, I plug in this over here. Now let us solve it for v1 final, for this variable over here. So we will see that v1 final is equal, Let me see. Let me actually write it with m1. So the whole term, this whole term, I'll move to left side. And then I will have here m1 v1 initial plus m2 v2 initial, these two terms, minus m2 v1 initial minus m2 v1 final, and this plus m2 v2 initial. But I have another term, v1 final, over here, so I can write that m1 plus, so this term over here, plus m2 v1 final, so I'm factoring masses next to v1 final, is equal, I can factor masses around v1 initial, so that will be m1 minus m2 v1 initial, and notice that I have this plus this will give me plus 2 m2 masses v2 initial. Or from here, now it's straightforward to conclude that v1 final is equal m1 minus m2 divided m1 plus m2 v1 initial plus 2 m2 divided by m1 plus m2 v2 initial. And this is now the result that we obtain for the v2 final after the collision. And notice it is given as a function of masses, which we know, and as a function of initial velocities, which we also know. Now what we can do, we substitute this equation over here, and we find v2 final. We will get that v2 final is equal v1 initial plus. Now again we can group terms around v1 initial and v2 initial to get that this is further equal. And now you can see that you can just sum these two terms and subtract these two terms. And if you do that, the final result, v2 final, will be 2 m1 divided by m1 plus m2 v1 initial plus m2 minus m1 divided by m1 plus m2 v2 initial. And this derivation is now completed because we have two final velocities given as a function of known masses and two known initial velocities. And this is how we describe elastic collisions in one dimension. In two dimensions it gets a little bit trickier because you have to look into the angles and vectors, but for this video at least we will constrain ourselves for one-dimensional perfectly elastic collisions. Now let us put these two equations into work and analyze a few very interesting cases, and two of the following three cases that we are going to investigate are particularly important for kinetic theory of gases and ideal gas in a box. So first, let us look into the example. If we have two particles that have same masses, this particle is moving with velocity v1 initial and velocity of v2 initial is 0. So the particle 2, this is particle 1, this is particle 2. Particle 2 is standing still and particle 1 will hit it. And let's assume, to make this applicable, let's say, to kinetic theory of gases, that velocity v1 initial is 500 meters per second, because this is an average speed of molecules in your room where you are sitting if you are sitting at room temperature and not at plus 1000 degrees or something like that. Perhaps in hell. At any rate, if we have this situation over here, our equations are telling us that V1 final, you will remember, was, well, because masses are the same, m1 is equal to m2, notice that this term will collapse to 0. But V2 initial is 0, this over here will be 0, which means that V1 final will be 0. So this particle will hit that particle, and after the collision it will lose all velocity. Particle 1 will lose all speed, rather. Now what will happen to particle 2, V2 final? Well, V2 initial is again 0, which means this whole term will become 0. But let's see what happens with this term over here. So this will become 2m, because m1 is m2, that's just m. m1, m plus m is 2m times v1 initial, and that's 500 meters per second. Well, these two cancel, and this becomes just 500 meters per second. So that means if this is before collision, after collision, if collision happened here, particle 1 stays with velocity v1 final equals 0, and particle 2 moves with velocity v2 final equals 500 meters per second. In other words, particle 1 transferred its kinetic energy completely to particle 2, and particle 2 continues at 500 meters per second. This reminds me a little bit like when at the Olympics we have rally and these guys are running around. So there is a person number 1 that is carrying this, I don't know how they call it, baton or a stick. So it runs, and the runner number 2 is waiting over here, and this guy approaches and gives this baton to this guy, and the guy number 2 continues running, whereas guy number 1 stays over here, and that's kind of elastic collision of runners carrying baton. But now case number 2, that is really important from the point of view of kinetic theory of gases, is if we have that particle 2 has mass that is much larger than particle 1. And what we mean by that is that really we are going to limit where mass of particle 1 is really 0 compared to mass of particle 2, or if you wish, you can say that mass of particle 2 is infinite compared to the mass of particle 1. And practically, from the point of kinetic theory of gases, this is usually important if we say that we have a box, and let's say there is a piston over here, and this piston is compressing this gas in the box. Okay? Now, let's say there is one particle that is going to hit the piston head on. Now, this piston has mass m2, and this particle has mass m1. Because it's a single particle, clearly this piston has mass that is much larger than the particle that is about to hit it. Also, the initial velocity of the particle is known, let's say. Initial velocity of the piston is 0, but also because this particle is so small, it cannot move the piston after the hit. The inertia of the piston is so large that one particle will not move it. So we can see that V2 after the collision is also zero. So the question is, what is V1 final? So what will be speed of this particle after it hits the piston and then bounces off? And this is important from the point of view of kinetic theory of gases, because we will use this principle in the next video to describe the concept of a pressure in the gas. Now, without postulating that V2 final must be zero after the collision, we can conclude that from this equation. Because in the limit case we can say that m1 goes to zero. Notice that this term goes to zero, because 2 times 0, this goes to 0, this term disappears. And V2 initial is already 0, which means that 0 plus 0, we end up with 0. So that's the rigorous argument that V2F must be 0. But what about V1F? Well, let's analyze that. V1F. So first, V2 initial is 0, so we can already see that this term will go to 0. But what about this term? If m1 goes to 0, this will tend rather to minus m2, and this will tend to plus m2, denominator v1 initial. These cancel, and we will get that v1 final is equal minus v1 initial. So, also kind of logical, what we conclude that this particle will bounce off the wall with the same speed but opposite direction compared to the initial velocity. Now, what will happen to momentum in this case? Well, change of momentum for particle 1 is momentum of particle 1 after the collision minus momentum of particle 1 before collision, and that is equal. Final momentum is m1 minus v1 initial minus initial momentum is m1 v1 initial, or delta p for particle 1 is equal minus 2 m1 v1 initial. And this is indeed very important result, because it tells us that the change of momentum is 2 times the initial value of the momentum. And that makes sense, because if the particle is going in this direction and after hitting the wall it has the same speed but is going in the opposite direction, that means that the amount of momentum that had to be given to this particle is 2 times the initial momentum. If it was just once initial momentum in the opposite direction, then the particle would just have velocity 0 when it hits the piston, but it doesn't have velocity 0. It returns with velocity that has the same speed as the initial velocity, which means that the momentum supplied to the particle is really 2 times the initial momentum, but in the opposite direction. And consequently, that also means that the momentum that is supplied to the wall is plus 2 m1 v1i. When I say wall, I really mean piston. And we will definitely use this result in the next video to investigate the pressure in the gas. There is one more case that is very interesting, and I will try to squeeze it here, and that's case number 3. What happens if we still have that mass number 2 is much larger than mass number 1, but initial velocity of particle 1 is 0? What that means is we have this container, we have piston. Piston is now moving, let's say some force is applied on the piston, and here there is a poor particle standing still, initial velocity is 0, and this piston is about to hit the particle. What will be the final velocity, or rather speed, of this particle? Well, if you go through these equations, and I'm not going to now do it step by step, you will see that V final of the piston is the same as V initial of the piston. And that makes sense, because this piston is so large that after it hits this particle, it doesn't even notice it. It just continues coasting with the same speed that it had before hitting this particle. But, very non-intuitive, what will be final velocity, final speed rather, of particle 1? Well, if you carry out this analysis over here, you will see that it is 2 times initial velocity of the piston. And this is really non-intuitive. When the piston hits the particle that is standing still, the particle will bounce off with the velocity that is 2 times the velocity of the piston. Here I am on the website of the Collision Lab, and I will put the link in the description so you can explore this website on your own. Let us start this one-dimensional, perfectly elastic collision. As you can see, we have 2 balls of different sizes and velocity colliding with the wall of this container and colliding against each other. The velocities are changing, but the value of the kinetic energy stays unchanged, 0.44 joules. So if we include velocities, you can see that the velocities are all over the place, constantly changing, look, after the collisions, but the kinetic energy stays the same. This is a beautiful laboratory where we can also change the mass, for example, increase the mass of particle 1, and now the dynamics is different. Of course, kinetic energy changed because we increased the mass of one of the particles, but now, after we changed it, kinetic energy is unchanged in these one-dimensional collisions. We can add more particles, and the dynamics will change. Of course, we increase now kinetic energy. There is one more particle in the system, but the total kinetic energy is conserved. 4 particles, even more mess in terms of the collisions, but kinetic energy does not change in perfectly elastic collisions. In addition to deriving velocities of 2 particles after the collision, we also revisited our knowledge of the conservation of momentum and conservation of energy. These 2 conservation laws are backbones of physics, so I hope that this video goes beyond simple one-dimensional elastic collisions, and it gave you insights into the conservation laws of nature. Until next video, goodbye.